Um, we're going to go back to chapter 11 and discuss that for a little bit. Um, Chapter 11 will be on the test, but it's hard to ask questions about this chapter other than um, a big question. I mean, like a massive question, and there you can't ask too many of those because you will run out of time. But the the kind of questions that you will find on a test are a little bit different than the kind of questions you'll find in the real world because this is a chapter that has a lot of applications that you'll find in the real world, and I wanted to go through some of those first. And so we talked about the other night about some processes lend themselves towards state diagrams and some don't. And we talked about the state diagrams for some things are trivial and some things are not. And if you see a process that has a lot of these in it, which are cylinders, either air, pneumatic, or hydraulic, you'll find that there's probably a good chance that you'll have state diagrams involved. So that's a tip-off, is if there's a state diagram involved, okay? We talked about before that if you are writing programs and you want to know whether there is a seal or memory circuit involved, you can say, is there a switch that I need that I don't have? In other words, I need to have a 2-position switch or something. I need to have a 3-position switch or something, but I don't have one. Physically, there's nothing available that I can use for that. And in those kind of situations, that's a tip-off that you probably will use a memory circuit. And here, when you see these guys, it's probably a state diagram. Okay? How many states are there in a cylinder? Well, there's typically 4, and I'll show you the state diagram for those here in a second. You can have different types of pneumatic cylinders and hydraulic cylinders. You can have 2-port, you can have 1-port, and you will run into different types and you'll run into different situations with these, but typically they're very simple from an electrical point of view. They're very complicated from a pneumatic point of view because you have to set them up so that they will exhaust and all that sort of thing. And if you get into that, I'm not going to talk about that tonight, but there's a whole series from a fellow whose name is Pytel, James Pytel, and he's the Big Bad Tech, and he does a whole wonderful series on how to set up pneumatic cylinders and hydraulic cylinders. So if you're interested in that area, there are some really good videos. I'm just not able to do them. When I see a cylinder like this, what I typically do is what I've done in the past. I will take 2 outputs. If there's two outputs in the program for this, I will take the program and stop the program, but I will force one on, then turn it off, then force the other one on, then turn it off, then force both on and then turn them off, and see what happens. Because it can be anything and everything how these operate. But again, I'm not trying to just say how it works, but this is typically how they work. There's the four states of a cylinder. Or you can be in the one position, you can be in the other position, or you can be moving from one to the other. And moving can be a state. Typically, a time is not a state. If you use timers, a time delay is not a state. We talked about a very simple state diagram of the two's complement program where you did the bring the 1 over, or bring the number over, bring the bit over, bring the bit over. But when you hit a 1, what you do is you flip, and all of a sudden from that point on, you're flipping the bits to the other. So that's a 2-state operation. You don't think of it as a state diagram, but that's a state diagram. Simple, but yet it's a state diagram. Okay, and this is a state diagram where you have a state where this is a loading conveyor, and then when you get full, it becomes an offloading conveyor. So it's either one or the other. It can't be both. Now you say, well, it can be. It's very difficult if you try to flip it back and forth between being a loading and an unloading conveyor when you still have boxes on it. So if you consider what we call to try to simplify a process, you always try to make it as simple as possible. You try to make this either a loading conveyor or an offloading conveyor, and you don't try to mix the two. Okay, and again, it makes it simpler. And the Simon Says program that you have in chapter 13 is you're either not playing or you're playing, and when you're playing, you're either showing the lights or you're letting them push the buttons. That's a state diagram. It's a fairly simple one, but it's a state diagram. And again, you can use sets and you can use Venn diagrams, although I don't talk about them other than right then, and that's as far as it goes. Now, there is a special language for state diagrams. It's called sequential function charts. Now, this was invented by the French, and it was first used in the 1990s by them. And since then, it has become a more popular language. But I'll show you one of the problems that it might have, and I don't know, you have to be careful of this. If you're in a specific state, you're not executing these other states, okay? Now, if you're in this state, you're not executing these states. If you're in this state, you're not executing any of these three states. There's logic in each of these states, okay? Now, if there is safety logic in these states and it's not being executed, what happens? That safety logic is not happening. It's not being exercised. So you have to be extremely careful, all right? So when this language first came out and it was being talked about, it's called graph set, okay? Graph set. And I asked the guy who was selling this, I said, now, how much of this actually goes into these various states and how much of it goes into an area they called P0? The P0 state, or the P0 area, was the all other area. And he said about 90% of the code went into the P0 area. So I asked the question, how good is this if 90% of your code goes elsewhere? He didn't comment. But you have to be very careful that anything having to do with safety is executed all the time. So if you're executing a program that this part is not executing, this part is not executing, and if there's some safety in there, you got to be very careful that you don't put safety issues in these states, or else it might cause a problem. All right, if you're not executing the code and it's a safety issue, it might not solve the problem if the problem occurs. Okay, so this is another set of it. I'm not trying to promote this as a programming language, but it's available. And if you are a math student and like matrices and you want to solve going from state to state with a matrix, you can dial up what we call Petri nets, which is nothing more than state diagrams using a matrix to decide when you go from state to state. So again, we're not using Petri nets and PLCs, but it's the same thing, except for the fact that the moving from state to state is a very complicated process using a matrix. And different types of buttons, I talk about that. And then a little bit about scan-dependent code, which I'm going to skip. It is kind of important, but I'm not going to cover it tonight because it's not something that I think is that important, okay? So here is another state diagram, which I probably would never use, but I did talk about it a little bit. Here is a state diagram that is very useful. This is something like your button arrangement on the garage that you might have for opening your garage. And this is a 3-digit, 3-entry, 3 numbers, 3 digits to get into the safe, okay? In order to do that, you have to go through a fairly sophisticated state diagram. You got to punch these numbers in order. Number, 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 enter, number, 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 enter, number, 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 enter, and then you open it. And if it works, it opens. If it doesn't, you have to go back and start over again. So this is a fairly sophisticated state diagram. That's typical state diagram type stuff, okay? But again, we want to talk about a process. And again, does this have cylinders? Yes, it does. It's got 3 cylinders. It's got this one, it's got this one, and it's got this one. It goes back and forth. So how many cylinders are there? There's 3. How many state diagrams could we have? We could have 3, or we could combine them into one. And I want you to understand that you can, if anybody ever asks you how to create some state diagrams from these, all you have to do, you count up the cylinders and make each a 4th state diagram, and you've answered the question. Although you may not have given the best answer as far as how to actually program them. But that's an answer to how to create a state diagram for that process. Okay? That being said, there is a better way, in my opinion, and that would be to what they call a runoff diagram. Now, here's another one. And here is a state diagram for that. Now, look what they've done. This is the German approach to state diagrams. You're in a state, and what does it take to go to the next state? They list the step that has to happen for it to go from this state to this state. Okay? Again, they don't always have to go in a circle. This is kind of going in a circle, but it also has offshoots. Sometimes you have circles, sometimes you have other things. Sometimes you have loops that go to loops. That all is part of it. And there's more than one state diagram for a process. There's the automatic mode, the manual mode, and the homing mode. There's 3 state diagrams for every process. Here is the standard state diagram for a cylinder. Okay. Now this is a shortcut for this is a cylinder. It's a riveter. But notice that it's only down for about a second or a half a second, and it comes back up. You remember, if it's only a short time and it's a time delay, sometimes you can get away without having to make that a state. In that case, how many states do they say there are? How many states are there? There's 3, not 4. So again, it's up to you. It's there's not a right or wrong answer. But you can use 3 states if there's only a time delay with the one state. It goes down and it comes back up. It's a 3-state device. Okay, here is this example I showed you the other night about 2 cylinders and the taking of those 2 cylinders and making them what we call a runoff state diagram. This is the way I've always programmed. I didn't program this way ever. The Germans convinced me that this is a way you can do it, but again, this is the way I've always programmed. I immediately did this, I didn't do this, and then moved to this. They want you to think like this, and then move to this from this. Or just program from these. And I refuse to do that. It's called a runoff diagram. Okay, now sequencing is a simplification of state diagrams. Sequencing is also synonymous in many people's minds with state diagrams, but they typically are in a circle only. It goes around in a circle, and that's it. Okay, so here would be a sequencer, or it could be a state diagram, but basically this is a sequencer. It goes around in a circle, and it goes back to home. Okay, now where do these get their names from? From drum switches, okay? Before there was sequencers and before there was automated systems, there was a thing called a drum switch. And it was like this, it looked like this. It was a drum, and it had pegs in it. It had holes for pegs. And if you put a peg in that state, it was on, okay? And then when you get all the satisfied situation in that one, then it would increment to the next one. So it would actually increment by 1 step. And that's called a drum sequencer. All right. Now the sequencer statement has leaked into the PLC, and Allen Bradley has a sequencer instruction, okay? They do have a sequencer instruction that works like that, and it moves like a drum sequencer. However, I've I've only used them very reluctantly, and I've used them maybe once or twice, but I'm not a fan of the sequencer instruction. The reason I'm not a fan of it is because it leaves you high and dry as to how to go from step to step, or from state to state. The documentation is just not there. Now, this approach is a better approach to doing a simple sequencer. And I did a lot of these, and I also warn the classes that I teach that if you are interested in working in controls and you get a job, let's say, or maybe you're going for an interview and they give you a test, this would be the kind of test they might ask you, okay? So it's a simple process. It starts here, it does this, it does this, it does this, it does this, and it goes back home. 4 or 5 steps. Now, what is the best approach to doing that? Well, I believe this is the best approach because it's something that electricians understand, and it's something that you can quickly come up with these. Now, this is the first step, and this is called the permissive string that gets you started. This is the things have to be in their home state for this to happen. So this would be the home state right there. For this to be able to start, you push the button that says start. Maybe this is one of these is a start button. I don't know which one it is, but maybe this button right here has to be usually one of these. So this may be your start button. All these conditions have to be satisfied. All right? Limit switches have to be satisfied. Everything has to be satisfied for you to start. But notice once you hit start, what happens? This bit seals. Okay? So here, but not here, is state 1. So this sealed, but not this sealed, is state 1. And what has to happen between state 1 and state 2? These have to be satisfied. Okay? So here you go down to here, and then these things have to be satisfied. And when these things are satisfied, then you go to state 2. So this bit is the first bit that turns on. It says this is your run bit. Okay? And it turns on immediately when you're running, and it stays on. Then this bit turns on. This would be step 1. Then after it's done, it's step 2. All right? So what are you doing? You're sealing these circuits as you go down, as you go step by step by step. This turns on, then this turns on, then this turns on, then this turns on, and this turns on, and this turns on, and they all turn off. Okay? Now, what have I not done? Where are the outputs? We don't know. They're not there, are they? They're not there. Why? Because outputs are not necessarily steps. Outputs can be on multiple steps. They can be on one step, then turn off, then come back on the next step or whatever. So you program the steps and then you program the outputs. Now, this is one of those times when you say, what did you just say? I said you program the steps and then you program the outputs. Well, how do you get it to work until you program the outputs? You don't. You gotta figure this part out and then turn on the outputs as you go from step to step. This is a simple, honest to goodness, one of the simplest programs you can do. And it's like up, down, this left, right, or whatever, and then you come back home. Maybe 4, 5, 6 steps, all right? And you're done. This is probably what they will toss you in an interview or maybe in a first day on the job. We'll toss them a bone and see how long it takes. And if it takes you more than a day, they'll laugh at you. I don't want that for anybody in here. I want you to be able to do this. I want you to be able to see how to do this. Okay? So this should have taken you 20 minutes. And they smile at you. Okay? This is something that is expected of you to be able to do. Now, the outputs are programmed later. They're programmed after you've done this part of it. And they come down here. They come at the end of this whole thing. So basically, it's a kind of around, going around a circle. It's like this thing right up here, just going around in a circle, and then done. Now, my rule of thumb is this. If you get more than 7 or 8 states, don't do it this way. Although electricians will not like you, what would be a better way to do this? Use numbers, okay? A numbering system, an integer numbering system. If you're in a state, you can't be in another state. So if you're in step 1, you can't be in step 2 or step 3 or step 4. So as you move from step to step, you start with a number of 0 is off, One is you're running, then 2 would be you're running and you're in step 2, 3 would be in step 3, 4 would be in step 4, 5 would be in step 5, et cetera, et cetera, et cetera. Now, electricians don't like this, but what's good about this approach? Well, if you miss and you have to add a step, it's a lot easier to add a step using a number. You can go out to it like you go 1, 2, 3, 4, 11, 12, 13, 5, 6, 7, 8. And that's easy to do. That's very easy to do with numbers, whereas if you're trying to do it with seal circuits, it gets very cumbersome and very complex. Don't do it with, if you have 10, 15, 20 steps, use a number, please. Don't try to do this with a seal circuit. Unless you're a real glutton for punishment. And at that point in time, I wish you the best. But as you get more complicated, I think a numbering system is much better than a seal circuit approach. However, with the real simple ones, electricians love you to death if you just say, do it with a seal circuit. And then seal, 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 done. Okay? Does that make sense? 2 approaches, same process, and each of them will get you there, but believe me, numbers get you there much quicker if you get a complicated set of whatever. And adding of time between steps is easy because what you do is you just add, your coil is not a coil, it's a timer. And when you get to the end, you time it out, you seal it, and then you move to the next step. That's all it is. So if you have a time delay between steps, then you just add these timers and you're done. Again, not a big deal, but it really is effective. Now the sequencer instructions can be done instead of the 2 types that I showed you below or above. They're called a sequencer output, which outputs the second of bits, and the sequencer move, which is the one that actually checks the matrix. And then, but you're filling in 1s and 0s, and you're filling in another one of don't cares. So you're saying these bits have to align. If they all align, then go to the next step. That's all it is. And believe me, this is not a trivial process to fill these 1s and 0s out. And it's also not a trivial process to try to figure one out if you're not the person that designed it. If you're the person that designed it and you've got a sheet that shows you exactly what each of these bits means, it's easy. But if you don't, it's very painful, very hard. So again, some people say sequencers are the answer. And other people say, I'll never use a sequencer because they're hard to troubleshoot. You have these 2 dichotomies, and some people like them, some people don't. I personally do not care for sequencer instructions. And if you follow the 2 main people, Siemens and Allen Bradley has it because they're mimicking the drum sequencer, the drum circuit. Siemens doesn't even have the instruction in their instruction list. I'm sure they have a function that'll do this. When I was over there, they were bragging. They said, we have 3,000 to 4,000 special functions in a library that you can look up and you can use. In other words, if there's an instruction that you don't find in the instruction list, we have you covered. We've got 3,000 to 4,000, and that was in 08. How many do you think they've got today? I don't know. A lot. I don't care how many they've got. They've got a function library of thousands and thousands and thousands of specialized instructions. So if you don't think that there's an instruction that will cover what you want it to do, I doubt it. I bet they've got an instruction that'll do it. Specialized instructions will do about anything. Okay? And we'll talk about in chapter 14 how you can build your own specialized instructions, function block instruction. We can build our own. This is the process that I talked about the other night that I was so enamored with, the idea that it worked and that they started it up and they understood it so quickly that I didn't ever have to go back. And I appreciate that. And again, there's the 3 main circuits, the 3 main, and there they are looped together. So you can kind of see that. Okay? In the back of the 1100 room, there is a machine that is very much like this, and it goes around and around and around, and it takes the part and it hands it off to the next part. It goes around and it goes to the next part, goes to the next part, goes to the next part, goes to the next part. So it does this. It does about 5 of these loops. If you want to do that for one of your projects, you're certainly welcome to. And there is the multiple sequencers and some of that. Now here is a pictorial of how state diagrams actually work. So you're in a car, right? And you're going to try to get out of from the movie or whatever. So you're turning out and then everybody moves up. Everybody moves up, the car moves out, car moves out, car moves out. And they just keep moving up one spot. Okay? That's how it's done. And there's the state diagram for that. And there's a machine that does that very thing. Okay. Now at the end of this chapter, there's a state diagram right there. It's a programmable one. Do you ever realize that? It's all based on time. What is that? That turns on your lights at night if you're away, right? It turns on like a lamp or whatever. It turns it on and turns it off. Makes it so that you can make it look like you're home when you're not home. Or turn on and off your Christmas lights or whatever, or your Halloween lights. And here are some of the state diagrams. This one is of an elevator, and I actually worked on this one when I was in Germany a little bit. I didn't do it the whole thing, but I did part of it. What would you say would be the overriding state diagram for this? And I know it's kind of hard to grasp this. But what would be the whole overriding state diagram for this? If you design around a very simple philosophy, you would say that is either going up, is going down, or it's an idle. Okay? And you can go this way, 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 and all that kind of stuff. But that's a very simple diagram of the basic philosophy of how this thing works. You may disagree with me. You say, well, it's more than that. Yes, it is. That you go up, you go from layer, you can go from floor to floor, and you can go this, you can do that, based on request, based on request, based on request, based on request, based on request. Yeah. But this is the basic diagram. If you agree with this, you pretty much can program it from there. They build these. This is one of the things that they had at Germany. They had these. They physically had these. They were plastic, and you could see in them. And they had the limit switches. They had the cab, excuse me, that went up and down. One of the things that's interesting about the Germans is, where's the first floor? That's first floor. Base floor. This is the second floor. You're one offset from the base floor. All right? So if you're in Germany, BF is your first floor. This is the second floor, the third floor, and the fourth floor. It won't be on the test, but I thought you might be interested. Anyway. And there's some of the pictorials of some of the stuff that they had. And they have more. We have some of these in our area, but this is some of the stuff that they had. There's one of them. There's one of them. There's one of mine. Now I wanted to get to this because this is an interesting lab. And if you want to do this, this is the physical challenge lab. Of all the labs that I have, I won't say this is the hardest one, but I'll say this will tax you as much as any of the labs that you have, okay? Now, I tried this one when I was in my prime, and I had to back off and recount a little bit. I had to back off and think about it. I couldn't just rattle it off, okay? Now, what is this? This is a 3-pump header. So basically, if you need more, you turn on a second pump. If you need more still, you turn on the third pump. If you need less, you turn off which one? The first one you turned on, right? Why do you do that? Why don't you turn on this one, then turn on this one, then turn on this one, and then turn this one off, then turn this one off, and leave this one running the longest. Why do you do that? Why would you do that? You'd wear out pump number one first, right? So if you just let them cycle in natural order and keep going around in a circle, they would hopefully get the equal amount of wear. All right. So the guy that asked me to do this for him, he started throwing things in there like I couldn't believe. But what it boiled down to was this. Yeah, you can do that, but you can also take any one of these pumps out of automatic and put it in manual and then start and stop it by hand. So if you take it and put it in manual, and you could have manual for here, and manual for here. If you take it out of auto, you put it in manual, then it is out of the automated sequence. So if you took this one and put it in manual, these two would cycle between them, two of them. Or if you took this one out of manual and this one out of manual, this would just cycle on and off by itself, and that would be it. Everybody follow that? So any of the pumps can be in auto, any of the pumps can be in manual. If they're all in auto, they cycle through like I just said. This is not an easy problem. This is just a logical, difficult problem. This is one that you will spend some time at. If you are interested in doing the physical challenge of this one, be my guest, it's a 4-point problem. It's worth every point of those 4 points because this ain't easy. This one's not an easy one, okay? You can't use sequencers. I mean, there's no magic 1, 2, 3 for this one because you can take one of them out and put it in manual, or two of them out and put them in manual. There's no quick fix. And here is the state diagram. Yeah, it is a state diagram of sorts, but there's not much. And here are the hints. Did I show the hints for this? Called a floating master. The hints are in here. There's some good hints. It's a good problem. I don't want to keep you on this too long, but I want you to understand that this is a good, hard logic problem. And I've said it many, many, many times to the various classes. If you can solve problems like this, you're well on your way, because this is not an easy one. The story behind this one, from my perspective, is this. Why I assign it all the time is because I don't assign it. I just say, if you want to do it, you can. The guy that I helped do this, we put it in and it worked. And the guy who was the maintenance foreman at the plant we were at, he took it out and he made it a fixed master because he said the electricians couldn't understand this system, this floating master system. The electricians don't understand it. I'm not going to put it in. He couldn't understand this. He didn't like it, so he took it out and made it a fixed master. Okay? That guy went to 3.5 years to Purdue in electrical engineering and then dropped out. So my challenge to you is, if you want to be better than the guy who went 3.5 years to Purdue and then dropped out, do the floating master and call it a day. I like to bring that up because I went to another school besides Purdue, but I like to bring that up about Purdue. So again, such is life. Anyway, that's my story. Any questions? Any other comments? Purdue's okay. Anyway, so we've got these old tests, right? And I put them up there, and we've got old tests. Old tests. Okay, so let's go back and look at some of these and see what we got. Midterm test, and this would be in, okay, that one right there. Okay, let's try that one. Okay. Oh boy. Okay, so um, some of these are pretty straightforward, some of them aren't. Go through, and again, I don't vary from these very much. So if anybody has any questions or want me to slow down, I'll slow down, but basically just want to get through as many of these as I can. So this one, pretty straightforward. Anybody have any questions about how to do this one? By the way, you have access to these. You don't have to just copy these down quickly. You have access to this file. It's in your where is it at? Is it in your yes? I can't hear you. What's where's that what now? Well, these are it's a file, and every one of them's a file by date, and you can see the date on them. This was 22, 23, I think. This one is this one is 10, 20, 10, 12, 22A. Okay, so any questions about this one? It would be A naught and D naught. I don't want to do all these. A naught and D naught. And then and now it's ORed with B and E. And it was and now it's ORed with C naught. And that was ORed, now it's ANDed with F naught. Would be G naught. Any questions there? Okay, so the following convert to seal, to a latch, to a set reset. So here you look for what is, here's the output and here's the feedback. So the signal here is the latch and the unlatch are the same as the set reset. So you would say A, B, and C. Would go to a coil. It'd either be a latch or a set, either way, and the coil's name would be G. And now the other side would be the stop part, and it's ANDed, so it would be ORed, so it would be the D or E naught or F naught. Be the unlatch or the reset of G. Same thing. Okay, here is one that you might see again. I don't know. I like these because they bring out all the stuff that we learned in the first couple of chapters 6 and 7. The material moves into the box with an arm that moves left and right. The sensors at each stop movement, and after a short time delay, reverse the motion. The operation is complete with 50 passes to left or right. Is noticed occasionally a photo eye goes bad, and the fastener continues to travel into the box, causing a crash. Okay, so the rules of the road are write the control logic first. Then go back and do the diagnostics second. Okay, so you push a button. Now, you have a choice. You can either, basically, you have to use a counter or a number. You can use a counter or you can increment a number in a holding location. Either way works. And I really don't care, but I like counters because they automatically count on a leading edge. You don't have to you don't have to do a first a one shot. So again, you push a button to start. What the heck? Okay, you push a button to start. And I don't know yet what's going to seal and what's going to make this turn off. Let's call it run. You have to do this. This is kind of the you got to do this. Okay, now when I run, the starting of the leading edge of the run is the setting up. You initialize things. Okay, how do you initialize? If you're using a counter, you would say go to 1. Okay, put a number 1, move a 1 into a thing we would call count. Let's move a 1 into a word called count. Okay, let's forget about this. Now, if you have a number 1, you're going to the right. If you have a number 2, you're going to the left. Now, notice what is going on. If you have bits in a word and they're odd, the leftmost bit is a 1. If it's even, the leftmost bit is a 0. Okay? So 1, 3, 5, 7, 9, 11, 13 is going to the right. 2, 4, 6, 8, 10, 12, 14 is going to the left. I'm using the bits in the counter to determine which direction I'm going. Does that make sense to everybody? That's a trick, but it's a very valid trick to do questions like this. Okay, so I'm going to say if it's a 1 or if it's an odd number, and that's the bit here in count. If count dot 0, if you're Allen Bradley, it's dot 0. If you're Siemens, it's dot x0 is on. I'm going to the right. And when I hit the photo eye at the end, photo eye at the right. Now I have to make a choice here. Either I hit the photo eye and I stay with the photo eye, and then I have a timer, and usually this will work. Again, I have a timer, and when that timer times out, what do? Increment my counter, add 1 to the counter. Count plus 1 going back to count. Now I'm going to the left. Oh, and the run bit has to be on. Count dot x0 off, and photo eye to the right, and photo eye to the left. Another little timer, and then what do? You bump the counter. Now you've got your control. You basically got your control. This is a timer, and you add count plus 1 plus 1 back to count. Now I'm going to the right, going to the left, back, forth, back, forth, back, forth, back, forth, back, forth. Now what else do I have to do? You have to count to 100, right? And when count equals 100, what do? You shut it off. So when count equals 100, do a bit called off. When it'll turn it off, it'll turn it off. Does that make sense? Yes, sir. No answers, just lots of questions. But this is the way you do it. Typically, this is a way to do this. Okay? Does that make sense? All right. Then you do the diagnostic. Oh, and by the way, how do you tie this? Now you've got this bit 1 or 0, and not the timer is making it going to the right. It's either a solenoid or whatever. So you have to have an output that says go to the right. So that to go to the right, you would say this and not this. So you'd say go to the right, go to the right. And this would here would be not photo eye. It would be an output called go to the left. Okay, something like that. Again, and how do I grade these? I use a 20-minute rule. If you can get your answer to work within 20 to 30 minutes of putting it into a computer and getting it to work, I'll give you the full credit for it. In other words, you got the basic components down. It's just maybe a little bit of finishing it off and you're done. And you can argue with me and we can say yay or nay, but if you don't have any of the basic components in there, I count off, it's 10 points, I count off 5 or 7 or whatever. If you try, I give you a couple, 3 points, but I don't give you very much if you don't have any of the major components in there. But if you got them in there, just don't have them in the right spot maybe or whatever, I'll give you credit for it. I look at it for a few seconds. I don't just skim over it. I look at it, but I don't get really, yes, sir. Names. Yeah, names are fine. And you can mix Allen Bradley and Siemens. I know that Allen Bradley doesn't have a one shot with a P in it, but you can put that in and you can use the Allen Bradley together with the Siemens. You can use the combination of the two languages because I do it all the time. I realize that they're different a little bit, but that being said, I get the idea. Okay, so what's the other part of this? So if you're running and a photo eye is not activated, so if you're going to the left, okay, so you're going to the left, and the photo eye doesn't get activated for 15 seconds. You got a timer that sits here and says, I'm going to the left, and there's a photo eye that doesn't get connected for 15 seconds. Okay, so no photo eye, right, and you get 15 seconds in there, that's an error, right? And that's how you do the diagnostics after you've done the control. And you put them into the process the best you can. That's all that is. It's not a big deal. If you don't do the diagnostics always, it's not, no, but I shouldn't say that because I built it right into this one. Don't always worry about diagnostics, but you know, whatever. Okay. A low pressure switch is added to a starter circuit, okay? Now, here is one that when you see this kind of, you should be tipped off right away that a starter circuit looks like this. You've got to start, you got to stop, and you've got to run, right? You got to run. This is the start, this is the stop, that's the run. What's wrong with that in this case? You can never start the circuit because you got a low pressure switch in there. So you have to add a low pressure switch, and you can either add it here or you can add it here, but you have to add this low pressure switch like that, okay? But you can't get around it. So you have to add a timer on here that does this basically, timer 1 done. And when it's done, it opens up. In other words, it's on until the timer is done, and you put the timer over here. Or this can be done a number of ways. I'll say that. This is not the sacred way of doing this. You can do it a number of ways. Here's my timer. There's a lot of ways of doing this question, and I've seen it done many ways, and I have to sit there and figure out if your way is actually going to work. But that being said, this one will work. But the key to this whole thing is spotting the fact that how do you get around the fact that you can't start a circuit that has a low pressure switch in it, or that has a, you follow me? It's the immovable object irresistible force. How do you get the thing started? We have to provide an alternate path until the time delay turns off, and at that point in time, after 30 seconds or so, 15 seconds, you should have pressure. And if you don't have pressure, turn it off. But until that time, bless you, that's how that circuit's done, or something similar to that. Okay? This is the kind of circuit that is very simple, straightforward, and ending up, you probably do, if you program at all, you'll do hundreds of these. Not 10, maybe whatever, but in a year, you'll probably program 100 of these. These are, as they say, a dime a dozen programs, but you got to be able to do this, all right? Now here is one where you're being asked to find the start and the stop part of the circuit, and I'm mixing it all up, and I'm also putting in something that's not a contact, but this is a contact. This is a contact. Okay, it's a go no go piece of the circuit, and basically how do you do the negative of a greater than? Less than or equal. Okay, so what's the opposite of a greater than? Less than or equal. LEQ. You follow me? So you do the start part with the not of C. That's the only part that does the start. The not of C is the start part. That's the set of the circuit. The reset or the R part of the circuit is this and this and this and this negated. So it would be the not of A or the not of D or the on of E, and then this other thing, which would be the LEQ of this other thing. What's the opposite? You have to ask the question, what would be the opposite of this LEQ? Surprise, right? You have to actually use math in a circuits course, in a logic course, but you do. All right, any questions about that one? Now here's a good one, because this has not a big deal, but it's one of the basic instructional. One of the reasons I like doing Siemens and Allen-Bradley together is because all of a sudden I can ask you, here's the way Siemens does it, how's Allen-Bradley do it? Here's the way Allen-Bradley does it, how's Siemens do it? This is exactly that example. It's a, how do you do the Siemens version of the timer EN, which is the left on coming in from the left. What is the Siemens? Timer 1.IN. Okay? Timer 1.IN. What about the .done? .q. What about the timer timing? They don't have one, so you have to say the .in, but not the .q is the timer timing bit. And you use the name timer 1 or timer 0, timer 0, timer 0 dot that, timer 0 dot q, timer 0 dot in. Now this one is one of my favorites, not because it is really all that exciting or anything like that, except for the fact that I got asked to write a book for Siemens for the American market. And I never did, and I never would. Why? Because I couldn't totally walk away from Allen-Bradley, the American brand, okay? So even though I talk a lot about Siemens, I'm not a fan of Siemens. But these people, other people did. They actually ended up writing a book about Siemens PLCs. And the only thing that they took from my book was this problem right here. It's smack dab in the middle of their book, and the only thing they did, they made these conveyors 3D instead of flat. But they did this. They wrote the exact same problem. And then after they did that, then Siemens made this their example. In their example, when you click on their thing and how to do this, the count up down, the CTUD, the counter up or downer, they use this example of this exact same picture to do their example of a CTUD. So instead of it working from the big boys to the little guy, it worked the exact opposite, from the little guy to the medium-sized guy to the big boys. And I kid you not, if you look at the example in the Siemens literature, right there it is. But I can prove to you that I had it first. It's neither here nor there, but that's the truth. Anyway, so how would you do this? Well, this photo I counts the boxes in, this photo I count the boxes out. So there's somebody in here that reads these, and they basically, boxes are coming in. That's like a UPS. I've never worked at UPS, but I can only picture. Boxes come in and they flop into a big blob of boxes. Somebody picks them up and puts them onto the conveyor and they go out, or not. But anyway, how many boxes are here? How many boxes are in this temporary storage area? We use a CTUD, okay? So the count up, count down, And then there's also a reset. How do you get this? A CTUD, right? And this is the count N. This is photo I1. This is photo I2. And there's a reset and all that good stuff. Now this thing has a name. Let's call this conveyor count. Let's just call this conveyor count. This is the accumulated value. And that's its name. So you have to give it a name. Okay? Now, what do you do with that? Well, you say conveyor value, conveyor count, and you would say equals 0. Or do you say equals 0? No, you don't. You say less than or equal to 0. Now, if you say equals 0, that's okay with me. I understand. But why do you not say equals 0? Why don't you say less than or equal to 0? Because counters can go negative, and they do. So if it's equal or less than 0, you want to basically reset it. If there's none in there, you hit it back to 0. Okay. So this would be conveyor count. That's this light right here, empty. And all these are a bunch of compare statements. Not empty, greater than 0, 50%, greater than equal to 50, 90%, greater than equal to 90. If 100 is your maximum number or whatever, see, it's for 100 packages. Greater than equal to 90, greater than equal to 100. Okay? So you have compare statements for each of those. Greater than equal to. That's it. That's the answer to that one. But that's the only thing they copied. I thought they would, for sure, I thought they should copy the stuff in chapter 6 because that was the stuff that really means stuff. But they didn't. They didn't do that. They just copied this. And no, I didn't get them for copyright infringement because I didn't copyright it, so it's just what it is. Now this is another one. This is a timer one. So this is, how do you start a motor? Certain motors, you just turn them on and they run, right? Other motors, they have to warm up or they have to go speed to speed to speed. So they have to turn on more. They have to go through stages where they turn off resistance values that will gradually let the voltage build up. In this case, there's 3 time delays. There's first this one, then this one, then this one. I think that's the way they do it. They do K2, K3, and K4. So basically, that's just a stage of timers. And again, no biggie. This is a run button. Run. Stop. You can't get away from it. This would be the start and the stop and the run. The pun. Run. Okay? When you are running, you have a timer. That goes to another timer. So this one goes to another timer. And then that one goes to another timer. And this one turns on this one, this turns on, this turns on, and you're done. This turns on K2. This one turns on K3. This one turns on K4. And you're done. Any questions about that one? 3 documents that give legal instruction for electrical panels in a factory. NEC, NFPA, 79E, and UL 508A. Okay, a ceramic maker makes a certain piece of pottery cooking for a long time. Write a program in ladder that outputs a set point to his controller when he pushes the start button. Okay? Now, this is a stinko problem. It's not bad. I did not explain to you how to do ramping, and I haven't. How do you ramp? Just get out there and start, right? Well, you have a counter that goes at a certain time, okay? So you have a circuit, again, with something like a run circuit or something like that. And then this is your run bit. And when you're running, you're actually it's a counter that keeps it's a timer that every okay, so it basically keeps doing this. It's a TON. It keeps turning itself with an output. Okay, so this would be to count up. Okay, and every so often it counts up by 1. So this would be my TON dot Q or dot done bit. So every time it turns on an output, it counts by 1, and this count up goes to a counter that ramps up, and that ramp, the actual, this is our set point of my ramp. So ever so often it increments by 1, and it keeps incrementing by 1, incrementing by 1 until you get to a certain point, and then when it gets to that point, it stops, and then it does this, and it comes back down. If you hit hold, it stops counting up. Anyway, that's all that is. But it's this counter and timer working together that give you a ramp. What it is, it's a stair step. It's like this. And you keep incrementing by 1 ever so often. And your rate of change is how long it takes to do this. You just keep incrementing by 1, incrementing by 1, incrementing by 1, incrementing by 1, or decrementing by 1, decrementing by 1, decrementing by 1, decrementing by 1, and that's it. That's all this is. It looks hard, but it is not. Now here you've got to ramp from a certain point to another certain point, and then you stop, and then you dwell, and then you come back down, and then you stop. Here you add up, count up. Here you dwell, and then you count down. Okay? So here, we're counting up until you get to a certain point. And at that point, you stop, and you set another bit. So, in other words, when you get to a certain point, you say, I'm done ramping up. I'm done going up. When you get to a certain point, and then you dwell for a while, for a time delay, and then you start going down. So you remember when you get to here, remember when you get to here, and then you remember when you're done, and then you shut the whole thing off when you're done. I'm not going to program the rest of it, but I think you got the idea. Does anybody have any questions about that one? Do you see how you count up? You keep incrementing by 1, incrementing by 1, incrementing by 1. That's a rate. That's a ramping function. Any questions there? Any questions at all? Okay. This one was one that I honestly was amazed at this guy. He got a $85,000 a year job in the interview, he had never, in Cleveland, he had never worked in industry or done anything at all before, but he answered this question. This is all it was. This is lab 2.1, okay? This is lab 2.1. And he answered that question, and he answered it right away, and immediately at the end of the interview, they offered him an $85,000 a year job. This question, that's all it was. Anyway, so it's not, you say, I don't know all the stuff that you know, or I don't know all the stuff about PLCs. Look at this. This question is one of the simplest questions in the whole book. Okay? That's why I made you write the terminal numbers on that quiz sheet, because if you can write that, and you can do this question if you can write those terminal numbers on the sheet. You can do this question. That's all he's asking. The start-stop circuit. Okay, enough on that one. We'll do another one real quick and then we'll stop. But I think this is you got the idea of these. They're not, none of this is rocket science. None of it is rocket science. What's the trick of this course? Just to get you into the lab enough so that you get interested enough in doing this. If you like doing this, it's a career. It's a good career. It's a very solid career. And maybe you'll do it 10% of the time, maybe you'll do it 30%, maybe you'll do it 50%, maybe you'll do it 90% of the time where you're programming these things. It doesn't matter, but it kind of is the litmus test. If you can do this, if you can do it at all, it raises your employability, your sales, whatever, and it does help. I know it does. I've seen it enough times. But again, um, I don't want you to feel intimidated, like I'm, this is the only way you can do it or whatever. But I want you to understand that uh, you do not have to um, do this all the time. This is not like you don't have to spend all day every day doing this. No, no. You get to do other things as well. So this is another, look at this, the differences between this one and the other one. Not a lot. This was a year before. Let's go back another year. Okay, let's go back to, let's drop the needle here in 1819 and midterm tests. There were two. Let's try this one. Okay, here's one that we had in October of whatever. Okay, here, same thing. Wiring, I'll give you a clue. I'm not going to ask you a wiring one. Okay? Now, this question here is a takeoff on the question that we did originally in chapter 5. But in this question, once you get to a certain point, you seal the circuit with the pressure switch. And you do not take the circuit off and you don't drop them out until when? These both go to 0. These both turn off. This is a little different than the chapter 5 question. This is, you go up, and if you go to a certain point, you don't get pressure, you turn on the next one. If you don't get another pressure, you turn on the next one. So you keep sealing circuits as you go. Time delay, seal another one. Time delay, seal another. And what turns it off is when these both go to off. Okay? That's it. That's a simple circuit, but it's, again, it's seal circuits. This is, with this pressure switch in here, it's a seal circuit. It changed it from being a straight logic to a seal circuit problem. And again, I ask you to fill in the I/O for this one. Very rarely do, but in this case I did. Okay? Again, what is the opposite of LIM? What is the opposite of that? Anybody know? Anybody remember? What's the opposite of LIM? Well, it's an LIM, but you turn the upper and the lower around. So in other words, the opposite of a LIM for the opposite of LIM 750 val 250 is what? LIM 250 val 750. That's the opposite. This is a 7. Okay? The negative of this is this. And here I'm asking for a convert. This is FBD, function block diagram. Convert that to ladder. You should be able to do that. You've done it before. Here's the famous TON problem. Here's one with an Allen Bradley from the Siemens equivalent of Allen Bradley. Okay, what would be the Siemens equivalent? What's the big difference? Compute becomes a what? Calc. It's a calc block. And the inputs are all on the left-hand side, and they're called N1, N2, N3, N4. And the values out here are val 1, val 2, val 3, val 4. And your equation up here, instead of val 1 times val 2, is N1 times N2 plus blah, blah, blah. And the output is the same. It comes as an output, and it's called out here, it's called total. It's outside. And that's it. It's the same thing, except it's different. But that's how you do a total. That's how you do a calculation in a Siemens. What was the license number of the instructor in the ArcFlash video? NFPA 78. That will not be on the test. Here's another one. Find the inverse of blah, blah, blah. I'm not going to ask that one. I don't know if I asked that one or not. My favorite, right there. Made me famous, right? And how much? Do you want another one? Are you done? We done? Yes. Huh? No, the question is, are your labs due? You have to do 20 points by the 1st of April. That's the due date. And I have not graded these. I'll get these graded and hopefully back to you by Wednesday night. Wednesday night's going to be a zoo. I don't want to pass these back on Wednesday night to you, but I will hopefully have them graded. And if you want to see what you got up until that point, but there's a lot of labs that are either out there in the wind or you haven't done them at all. One or the other. You owe me 20 points by the 1st of April, and then you can do 20 points. I keep 2 grade sheets, by the way. Honest to goodness, I keep 2 grade sheets. I keep the before April, and then April 1st. I keep one after April 1st. So you got to get it. If you want to get it on the first one, you got to get it on by the 1st of April, or get an extension of a day or so, and that's it. I keep a separate one for the after April 1st deadline. So again, it's how we do it. Take care. I'll see you on Wednesday night. Take care.